Let me, the microphone works, huh? I think. You hear me in the back? Good. Then I just got permission from Valerio to start, even if it's not yet 9:30, because we are all sitting here, and I think, well, why not just start? Then we have something to do. So maybe I should step on the podium then. And I am Bas Edikshoven from Leiden in the Netherlands, and I teach one of the courses here, not just by myself. There is another teacher, she will come a bit later, that is Intan Muqtadi. And that is, I even don't remember the title of my course, I think, but it has to do with group actions that come from geometry. And in the end, we will use techniques from another course that you will see on representations of finite groups to a group that comes from the real world, namely the group of rotations in dimension 3. And we apply it to do Fourier theory on the two-sphere. So I think you think this is a conference and a school about algebra. It still work? Yeah, okay, good. I didn't hear myself through the speakers. So you think this is only about algebra, but a good thing about mathematics is that all parts are related. And whatever is done somewhere is used at other places. And so the algebra you learn here can also be used to do Fourier analysis, like you know on the circle or periodic functions on the line. You can also do that on some object like the sphere in dimension 3, on like the surface of the Earth, right? So, and that is not so obvious how to do Fourier analysis on the, there are two coordinates, and it is not the circle times the circle, it is a bit different. So that is the goal of this course that I teach with Intan, and but first we start with something that has to be done at the beginning of this course, namely what is a group? The central object of this whole school is symmetries, and well, symmetries is a, we should define what they are, but look at my tag. If I turn it around, I think it's the same. Eh? It's made in a symmetric way, back and two sides. And that's an example of a symmetry, and that is like this. You stand like this, and you turn around. Well, I mean, look, yeah, those rotations are symmetry, and we want to make that precise in a mathematical terminology. So let me start with a definition. Ooh, I have to. How do I break it? Ah, you see, definition. So a group, and maybe you think, well, I have already learned what a group is, and I think that is true, but it's still good to start the definition so that we all agree on what we are talking about. A group is it consists of three things, actually. It's a triple. It should be, so, a G, a dot, and an E, with G a set. Is this still big enough for the back? Yeah? Everybody has good eyes. So G is a set, and well, you know that we have also, as mathematicians, laid down the rules for set theory like 100 years ago. So if you ask questions about sets, I think I can answer them, but I'm not going to do that now. I mean, to go into it. So G is just a set. This dot is a binary operation. So let's say a binary stands for the fact that it has two arguments. Binary operation on G, and so this dot is a map from G times G to G. And this is the product of the set with itself, and this dot is a map. And I think if we encounter the necessity to say more about what maps are, that will arise naturally. If you have an element in this product, it has two coordinates, x and y are elements of G, and our notation for this map is that we denote the image like this. That is what we do, so that is what this dot is, and E is an element of G, and this is called the unit element. So here are what these three objects are: set, a binary operation on that set, and an element such that, and now come the group axioms. So this, I think, what do I think is the most important condition? That is that this operation is associative. And I'm going, so for all x, y, z in G, you can compute the product of x, y, and z in this order, in the order you want. So x times y and then times z, this is the same as doing first y times z and then times x. That is called associativity of the product. That's, yeah, okay, such that maybe here I have my first property and then I have a second one. E is the unit element, so this E stands for the unit element, neutral element. So for every x in G, E times x is x, and this is also x times E. Okay, and the third condition is that every element has an inverse for this operation. So for every x, now, again, for every x in G, I think this, I should put it a bit higher. So, I hope, well, okay. For every x in G, maybe it doesn't work, eh? So where, yeah, still good? Okay, for every x in G, there exists a y in G, such that x times y is E, and that is also y. Oh, you see, I did something that I wanted to say, that we very often we just denote this just by xy, right? Okay, and I do it, right? It happened by itself. Okay, so this is the end of the definition of a group. I hope I didn't forget anything. And to confuse you, sometimes, or very often in fact, this dot is not at all a dot. Sometimes we use other. In the case when the group is commutative, if for every x and y in the group, x times y is y times x, then we call the group commutative. And in that situation, it often arises that the group operation is written with a plus. So here, this dot here, or plus, if G is commutative. So that can also happen, and that is only to confuse you. Okay, so these are groups. And maybe a first remark to do, that is that, oh, I could maybe, let me practice with the eraser. Okay, you see, there is a slight problem. Here I could say if you look at this thing, for every x there is y such that x times y and y times x are equal to e, then this y is unique, such a y is unique, and denoted x to the power minus 1, x inverse. If it is unique, then you can give it a name, and we use x inverse for it. Denoted, okay. Right? And so all the rest of these 2 weeks is about groups. And so maybe we should do examples to start with. Well, maybe even before, yeah, well, maybe first without writing it down, I give you an intuitive, not precise example, namely the symmetries that this school is also about. You have 2 symmetries on the same set, on the same space, and say in the plane or in a 3-dimensional, in R3 or in R2, you can compose them, because symmetries are maps from some object to itself. And we can compose, we know when we can compose maps. If F is a map from a set to itself and G is a map from the same set to itself, then we can also do first F and then G composed F. And that is an example of such a composition, a binary operation. And then the identity map from the set or this space to itself is the neutral element. I also maybe make the remark that I included this E in the notation, but if you think about it, I could also have left it out and formulated is saying that there is an element with this property because this E is also unique if you have these axioms. Huh? So if you have these properties, these 1, 2, 3, then this holds. So to show that this is unique, you need more than just number 3. You also need number 1 and number 2. And if you have these properties and also this unit element, there is no other one. And that isn't, yeah, I think in the basic algebra course, you learn that from the start, but I have no idea what all your backgrounds are. Maybe some of you come from more applied universities, and then they have probably never bothered to prove that. But such an E is unique, and the proof, you should certainly do it. So you have 2 elements that satisfy this property number 2, then you can prove that they are equal. Maybe you still have to use, no, I don't think you even have to do that, right? I mean, yeah, that is just this 2 by itself will let you prove that if you have E and E prime both with this property 2, then they are equal. Because you use it with E, and then you get E prime. Well, and you use also the same thing with the property, well, with E replaced by E prime, you will get it. And I hope really that if you have trouble with this, that you ask me in the training sessions how that works, right? The training sessions, I hope to have a lot of interaction with individuals, and I'm looking forward to that. And, yeah. Okay, but here, yeah, I think it is very hard to do that. So what I wanted to say just was that symmetries are examples of groups because you can compose symmetries, and it is that symmetries have inverses. If you do a rotation in the space, you could, over some angle with some axis, you can use the same axis but the opposite angle to go back. So it is always a matter of going from one situation to another one that is reversible. You can go back, and that is this invertibility in the last property. So, okay, so one example I want to, so the very first example, so let's say example 0, right? Example 0 is, let X be a set, or I would say for X a set. We take the set by sim_x, and sim stands for symmetries, and the set has no structure. You cannot say that it preserves something like distance or whatever, but of all maps f from x to x that are bijective, such that f is bijective. So bijective, that means it is injective and surjective. The easiest way to remember is that every element in the target has exactly one pre-image. So for every, maybe bijective, I would say for every y in x, there is, and now I will abbreviate, there is a unique x in x with f of x is y, right? So these maps we want to use, and you see in this definition, you see the inverse map already, because it says if you have such a map that is bijective, then for every y in here, so y in here gives me f inverse of y here, because of this property that for every x, for every y in x, there is a unique one that in the pre-image. And so the map f inverse goes like this, and we have for f in sim x, f inverse going from x to x as well, with, well, this f inverse is also bijective. Well, let's say it like this. F inverse, so this is my notation for composition maps, right? This is the identity on x. This is the identity map from the set x to x. It sends every element to itself. F composed with F inverse. So you see that this is perfectly satisfying these conditions. Well, the associativity, so composition of maps between sets is associative. So this sim x with now this little composition symbol with the identity element, the identity map from x to x is a, and this is called the symmetric group for the set x. For example, so if x is the set 1, 2, up to some natural number n, then denoted by Sn, okay? We denote it as n, and this is your first example of a group, I think. There are many more examples, so let's do, oh, maybe before I do more examples, we also want to know if two examples are the same, right? But another set, like 0, 1, say I take y equals up to n minus 1, right? This is also a set with n elements. And so what do we think? Are sim x and sim y the same in some sense, right? I think maybe I should put this in between. They're not the same because, strictly speaking, they are, the elements in sim x are maps from this set to itself, and the elements in sim y are maps of this set to itself, so they cannot be the same. But the same in, so what does that mean? So here, can I compare sim x and sim y? So what we can do is this. We can somehow identify these two sets. How do we do that? Right? They have the same number of elements. And actually it is very easy to choose a bijection between, we have, let's say that we do x, well, okay, good. F from x to y, sending an element m to, or maybe x, little x to x minus 1, right? That brings me from this set exactly to that set, right? If I take an element here and I subtract 1, I am there. And I also have g from y to x that sends y to y plus 1, right? Then I can go from here to there. And what I just did, these f and g are inverses of each other. If I start in x and I subtract 1, I come here, and then I add 1, I come back. F composed with g. Now I have to think. If I first do g and then f, then I go from y to y. So this is the identity on y. And g composed f is the, and given that I now have explained how I relate these two sets to each other, I can also transport a bijection, an element in sim x to an element of sim y. So this gives, okay, good. So that gives sim x a map to sim y. And how would I bring an element of sim x to sim y? So let me now call such an element sigma. And can everybody see this low? Yeah, huh? Is this visible? Yeah? It's border. Then I will. Is there a better way of cleaning this? It's not really working, eh? Yeah, well, let's try. Maybe if we write a lot on it, then it will all be whiter. You will not. Maybe, well, this is also a way to remember the definition. So I want to go from sim x to sim y. And if I have a sigma in sim x, what can I do? Well, let me write here this diagram, right? I have this f from x to y, and I have a y, I have this g going to x again. So if I want to, if I have a sigma, so you see, composition of maps we write such diagrams, and of course that doesn't add anything really to the understanding of what happens, but visually it makes your life a lot easier to write down things. The data you have in such a diagram helps to do something with it, because okay, so I have a sigma, so I also include it in the diagram, right? Sigma here, and now I want to go from y to y. Oh, that is then I better put it in the other direction, I think. You see, because I want to compose these arrows, yeah? So here I have a map now, so that gives me first G, then sigma, then F, right? So G, sigma, F. And I will not write the composition signs all the time, right? So this, and I compose, all the maps I compose are bijections. And if you compose two bijections, you get a bijection. So we have that. Okay. And we can also, if I have, say, an element tau here, we like Greek letters for some reason. So then I can also change this diagram a little bit. I can say, well, suppose I have a tau from y to y, and I will put it in the diagram like this, and I can do f tau g, right? F, then tau, then g. And these two maps, if you compose them, you will see that, so exercise, well, so these two maps, maybe I should call, oh, actually I have a map here, maybe I should call it phi, and here a map, I should call it psi, right? I have this one that goes that way and the one that goes the other way, show that sim x and sim y are the same after translation, and this is translation in the sense of language, not in the sense of a translation by an element in a vector space. After translation via phi and psi, right? What I say is, if I have two elements here and I take their images, I could multiply them here and then take the image. So phi, okay, maybe I should say, for every sigma 1, sigma 2 in sim x, phi of sigma 1, sigma 2 is the same as phi of sigma 1 . So here, and here something happens, and this is important. This is now bringing us to the notion of isomorphism of groups, right? This says that this phi brings, this is actually a multiplication in sim x, and this multiplication that I didn't write is in sim of y. Okay, so what happens here is that these two groups are not literally the same, yes? Did I write it wrong? Oh, I have twice the same. Yeah, you see, you have more, you are at a distance, you see the difference, and I don't. Or actually you see that they are not different, and that is wrong. So when I start with a tau, oh, the first one is wrong, right? Because that was going from, this should be a G, and this should be an F. Thank you, Muhammad. Now correct? Okay. So what I was saying is that these two groups are not literally the same, but these maps give a translation. So somehow, informally, I would say they only differ in an administrative way. It just depends. The elements have other names, but that's the only difference. And so you could, so what I try to, so here you see that you find the notion of isomorphism of two groups. Is it worth that I define that? Or how many of you, so everybody who has seen the definition of homomorphism of group and isomorphism, can they raise their hand? Then I can see, well, that is not very convincing. I asked everybody who has seen it, huh? But still, okay, no, people hesitate, so I should, then there is nothing to do. Then giving that. So, okay, so if, here is another definition. For two groups, G1 and G2, and so you already see that I leave out the composition of G1 and the identity element. Homomorphism, a group, let us G1 to G2. G2 is a map F from G1 to G2 such that for every x, y in G1, f of x times y is f of x times f of y. And here the same thing happens. The first multiplication here is in the group G1, but after you do f, you are in G2, and it is the multiplication in G2, right? And they are related by this map. And that is called a group morphism. I think in all the books that are more than 50 years old, you will, it is exactly the same thing. And you can do the exercise yourself, that if this is true, then also the F sends the identity element of G1 to the identity element of G2. Okay, and so what we have shown here is that, well, if you do the, I said that this is true. I did not give you the proof of that, but you can do that yourself, and if not, then you come to me in the training session. That these two groups, sim x and sim y, are isomorphic, right? And a morphism. So yeah, actually, if moreover f is bijective, then we call f an isomorphism. Okay, right, and now my chalk is gone, so I get a new one. Okay, good. an isomorphism of groups. Okay. Oops. Okay. So now we have seen the example 0. Example 1. I want to do some... Okay, this side. So let us look at what you are maybe more familiar with. So we look at the real numbers, right? This is the notation for the real numbers. We take R2, which is the set of pairs, right? It's the real plane. It is the x comma y with x, y. Well, it is, maybe I should just say it is R times R, right? It's the product of R times R, and so it is the set of pairs x comma y such that x and y are real numbers. And this is the mathematician's simple description of what people used to call the plane. But yeah, the plane, I don't know. That's something that for me is not well defined. But R2, I know numbers, right? So I think nowadays mathematics describes everything in terms of numbers. And so if we want a plane, we say, well, you have in the plane, you could take 2 coordinate axes, and then every point gets coordinates, a pair of numbers, and that gives a bijection between the plane and R2. But here we know what we talk about. So this is, for me, the plane, and we can give it different structures. We can view it as a vector space. I would say a vector space over the real numbers, an R vector space. That means that we use an addition. So actually you see the notion of group coming back right away, because that means that we have an addition. So x1, y1 plus x2, y2. To do a vector space, I first have to have a group structure 2 where the group operation is called plus. So we have this is by definition x1 plus x2, comma y1 plus y2. Okay. That is the addition, and it becomes, well, you know, addition of numbers satisfies all the properties of a group. The identity element is the 0, and the inverse is minus x. And you know also need for every lambda in R, so when you have scalar multiplication for every xy in R2, you define lambda times xy to be lambda x, comma lambda y, right? Where this is the scalar multiplication by scalars on your vector space, and this is the multiplication of real numbers, right? So you have that, and we can, so maybe a good example of a group. Now, I hope there is some, okay, actually it improves, right? After a few lectures, the blackboards will be white. Okay, so then, yeah, what we can, okay, so then we consider now I'm a bit, so I want to look at the set of transformations of this vector space to itself. And transformations, I think I would like to use the word symmetries. So I want to look at all the bijective maps from R2 to itself that preserve this structure, right? So we want to, so we consider, and then we give it a name. consider the set of linear maps, so F from R2 to R2, such that first of all, we are doing symmetries here. F is bijective. That is one thing I really want. And because we look at an addition and scalar multiplication, I also want that F is linear. Right, so I was doing groups, but now I'm doing linear algebra. Linear means that, well, should I? Let me do it. F is linear, it means that if I have, okay, for every x, y, and now you see I do something nasty. Up to now, x and y were real numbers, but now they are pairs of real numbers. Eh? And for every lambda in R, I have f of x, say x plus lambda y, is f of x plus lambda times f of y. Right? That is what you call a linear map. Okay, good. And bijective and linear. Yeah, okay, so I think I can. And so now the question is, how do we denote this set? So shall we call it out for automorphisms of R2 with the plus and with the scalar multiplication, right? I think that is a good name, right? This is by definition this set, because I take the bijections from R2 to itself that are compatible with the plus and compatible with the scalar multiplication. We call it like that. And actually, the first thing you can remark is that if I compose two things like that, that I again get a bijection that is linear. So this is with composition. This is a group. Oh, and because the inverse is also like that, and again the neutral element is the identity map, right? So I can compose it, but maybe you know this group already. Well, it is the same in the sense that it is isomorphic to a group that you already know. So is there anybody who has a suggestion how we can also, up to some administration, describe this group? No? Yes? The? Matrices? Yeah, okay. So, yeah, I get the answer. So, well, so the answer is that you can describe it in terms of matrices, 2 by 2 matrices, and then it becomes very concrete, because what I write here look like very difficult things, but in your linear algebra course, you have learned that every linear map between two vector spaces is given by a matrix if you happen to have a basis in each of the two vector spaces. But so every such F is given by a unique matrix A, let's say, maybe you use a capital letter, A in, and actually M2, 2R, so these are the 2 by 2 matrices. Every linear map is given by a matrix, goes to A times X. Now I have to view X as a column vector, right? Right, so this is what people in linear algebra always do. when they write it in the text, they write row vectors, but when they want to matrix multiply like this, yeah, then you cannot put a row there, you have to put a column there. Okay, and I do the same horrible thing. Okay, so this is what you learn, but in this case, actually, it is not yet true that every A in the matrices here gives a bijective map. So the map, this map, so, but even I can change this a bit. I can write here what the person who gave the answer to my question already. So this is GL2, general linear group. I abbreviate. And this is the ones where the A of invertible 2x2 matrices. And maybe you like to be reassured that a matrix, a 2x2 or an n-by-n matrix is invertible. You know, you have a criterion for that in terms of the determinant. It means that the determinant is not 0, right? That A is not 0. Then the matrix has an inverse. So this group is isomorphic. So, and we usually use, so this is the notation for an invertible map. It is isomorphic to GL2 of R, where what you also learn in linear algebra is that composition of linear maps in terms of matrices corresponds to matrix multiplication, right? So now the group is just, so this is the set, to write it out completely, say A, B, C, D, in M to R, such that AD minus BC, and you multiply such things, and that is, and now I have, but this I would claim, this is linear algebra, and my job is to do some geometry. So what is wrong? In the plane, we view this R2 now as a vector space. So we have an origin in it. We have the point 0, 0, which is the neutral element for the translations. But actually, for a geometer, one point in the plane is as good as any other point. So, and what is the justification of this statement is that if I have one point and another point, I can bring the plane to itself by translating this point to that point. So if I have a point x and a point y minus x, I can translate by the vector y minus x the plane, and then x goes to y. So that, and this translation, I can also undo it. I can translate over x minus y and bring y to x. So for a geometer who is not necessarily interested in the vector space structure, you should include these translations. So we also want the translations. And that is my next example of a group. So going out of the linear algebra, it's geometry. So we want to include the translations. So for every x in R2, or say, yeah, or maybe we have, well, I define something, right? Tx, T stands for translation. Tx goes from R2 to R2. And it sends, well, I cannot use the letter x now, so I use y. Y goes to x plus y. right? Or maybe, well, I could also write y plus x, that depends on what, but it's the same. So this is the translation, and you could ask what kind of, set of bijections from f from R2 do I get if I compose linear f's, so elements of, say, GL2R, this is now the shortest notation I have, right? These are these maps that are linear, and I think of it like transformations, but I write them as matrices with translations, right? With these TX. And compose, right? If I compose. So I can compose and compose more and compose more, and in group theory language it means what is the, you could formulate it like this: what is the subgroup of, and now I write down a horrible thing, sim of R2. So all the permutations of R2, so this is huge, right? It's very big because we don't ask anything, you just permutations of the set. And that set is very big already, so if you like set theory, you could try to see what is the cardinality of that set, and you can check it with me in the training session. What is the subgroup of that? Generated by GL2 R and the translations TX for X in R2. And I think my time is almost up, so I'm not going to do the exercise, but I give you the answer. The answer is, so you get the answer. You get the affine group. So it is the set so how do I, it is the set of F of the form, so these F go from R2 to R2, say an X goes to AX, A times X plus B, where A is in the matrices and the B is in R2. So you can, you get these maps. So these are called affine maps, affine transformations of R2. And actually the group, if you have a map of this, if I have an A and a B, and an A prime and a B prime, and they give the same map, then you can prove that B is B prime and A is A prime. And so it is isomorph, well, it is as a set, well, okay, notation, let me say, notation, we call it affine group of R2, affine group to affine transformations, and it is in bijection with GL2R, well, maybe I write it with R2 times GL2R, because every such map is given by an A and a B, and you put the A here and the B is there. But when you compose, something interesting happens, because it is not that you just add. If I have two elements here, I have A and A1, B1 and A2, B2. And if I compose, I do not get just A1 times A2, comma, B1 plus B2. There is something else that happens, and we will see that some other time, right? And yeah, okay. So my time is up. Thank you for your attention.